Thanks for the introduction. So I will be giving this talk on how can we achieve human-level AI in the distant future, because I don't think it will happen anytime soon. But at the same time, it's a super exciting topic for me, and of course, it will be in large part about language, because that's what I'm excited about. That's what I've been working on during my PhD, and as it was already said, I was working on this deep learning stuff for speech recognition, machine translation, and so on with recurrent networks, among the first people. What actually is this AI thing? I think that just the term itself has many meanings, because there are people coming from different backgrounds who actually think that it can be something radically different. Like nowadays, even very simple statistical models are often called AI, and that can be quite confusing, especially in the media. There's this confusion. So for this reason, actually, during the maybe last 30 years, different researchers did come up with many different names so that they would distinguish what they are doing from what is this big label that basically AI means pretty much everything that has something to do with statistics these days. So that's basically the reason why we have these human-level AI and general AI and strong AI and AI complete terms, and there are probably a couple of others that I don't know about. But it usually is basically a way how people can distinguish what they are aiming to achieve from what is being done. A simple test is that basically we don't have real AI at the moment, and if somebody shows you something that works, then probably it's not AI, but more like applied machine learning. So then there are, of course, people who will be showing you these graphs, how things are going very nicely, and we are very, very close to achieving AI. I think this is coming from Ray Kurzweil. Basically, the graph is showing that the computational power is that you can buy for $1,000 is increasing exponentially over years, and there's this prediction that by the year, I think 2100, we will have more computational power available for $1,000 than there's probably atoms in the universe. So I don't know if it actually will hold. Well, you can think of it something yourself, but usually when you see these graphs, then it's often hugely misleading, because first of all, the exponential growth never lasts forever in whatever environment. And second, we actually don't know how to simulate even these simple brains of insects and some higher animals. This is completely out of our current understanding. And talking about how much computation you need to do this is really science fiction. So I really believe that we still need research to be done to achieve AI, and there's actually a lot of difficult topics that we need to work on. Actually, in the last two talks, many of them were already mentioned. I can just say what even should be the objective for AI. Let's imagine that we will build AI, say 10 years from now. How will it look like? What will it do? What will be the goal of this AI? What computational model will it be based on? Will it be a neural network or some Bayesian model or something else? These are questions for the researchers, and actually we don't have any good answers. Actually, I can say that for all these basic questions, the real answer is that we don't really know. We don't even know how to model, for example, memory. It seems very simple that humans without memory would not be intelligent, right? And many of the state-of-the-art techniques that we have now don't really have any long-term memory. Even, for example, recurrent networks that I was working on for many years, and that are actually very interesting techniques on their own. And for example, even improve machine translation. These days, if you did see the jump in the accuracy in, for example, Google Translate last year, between English and Czech, it's a great thing. And I was actually at the beginning of the project at Google, but this is really applied statistics. These models that are behind these translation systems don't really have memory, and there are big statistical models that can read much more data from the web that a human can do in a lifetime. So they actually are very interesting from some point of view, but it's really aggregated statistics. It's not AI. So there's also a good possibility that whatever we've been working on as AI researchers in the last maybe 70 years or since the field started, that we didn't really find the right ingredients of like what needs to be put together so that we would like have this good plan for achieving AI. It's also interesting that usually when somebody is very optimistic, it's usually the junior people who are just starting working on the field, because there's this illusion when you start working on artificial intelligence that things seem to be almost like reachable. It doesn't seem to be a complex topic like intelligence, but the older the people are, the more time they spend on this topic, the more pessimistic they usually get, because in the end you just end up realizing that we don't really know many of the very basic answers to basic questions. So to give some like overview, like this roadmap, because this is the roadmap section of the conference, I will try to describe like how is the research currently like going for some of the people. Like deep learning is actually a cool topic that was like a research problem 10 years ago, how to correctly train these big deep neural networks that some of us did believe have a lot of potential. Actually, I must say that 10 years ago, when I was a PhD student at the Brno University, the number of people who didn't believe that neural networks have potential in these tasks, like say machine translation and so on, it was actually very few people. And it's interesting that usually majority of the research community is working on something that already works, and real research topics is something that is like very difficult to work on, and often even gets rejected by the mainstream. So the neural networks nowadays are actually very useful, as I said, like speech recognition, machine translation, image classification. All these tasks did improve greatly by using neural nets, artificial neural networks. But there's this thing that actually these models are often used, are often trained in a supervised way. That means that you have to tell these models, you have to show them many training examples where we have to show basically some, say, image or sentence, and then we need to show them a label, and the label has to be produced by humans. So this is kind of like a trick, and I think that people who don't have the machine learning background can often fall for this like some magician's trick, when you see the output of the machine, and the machine can, for example, be saying something that seems to be very insightful. It can be a joke, it can be some very complicated sentence that describes some image or something of this sort. And the issue with this is that often you are actually looking at a text that has been produced by another human, and it's part of the training set. So the machine just repeats what it did see during the training phase. So it's kind of like a super parrot or some kind of like a mirror that doesn't understand anything. It's just repeating what other people did tell the machine. So to just give you example, like many of the state-of-the-art systems, say for image classification, are trained on millions or even more supervised examples, when there is this huge database that cost tons of money to produce, where like hundreds of people did work for a very long time to annotate millions of images and write what they see there. So it you often, like, if you see just the end result and nobody does tell you what amount of work did go into these systems, it can look like intelligence to you, but once you don't know the magician's trick, then you may realize that this is basically just some nearest neighbor search, when for every test example you just find the most similar image, annotated image in your training set, and you just repeat what the label the human actually did annotate the image with. So that's like some warning to like interpret correctly the achieved results. They can be very interesting and useful for some tasks, but at the same time I wouldn't call about intelligence when it comes to whatever we achieved so far, because it really is the intelligence, the perceived intelligence is coming from other humans. This is just to convince you that the deep learning actually doesn't really have that much to do with the biological brains. The name sounds very like interesting on its own, like artificial neural network that really seems like we understand how the brain works and we are simulating a brain in a computer, but that's not really the case. This is the basic computational unit in a neural network. It's called a perceptron model. It has been proposed, I think, like in the 50s in the last century or sometime around that time. And it's actually very basic. You have like n inputs to the neuron where there are some real values coming in. These get multiplied by the weights, and actually the point of training is to find a good set of weights that optimize some objective function. Then you apply nonlinearity, which can be just a simple max between 0 and the value that you computed. And the output is sent to the output part of the neuron. That's basically it. And the neural network just is composed out of many of these units. So you can really think of the artificial neural networks as some nonlinear data projections where you represent the data as some fixed size vector, then you apply like data projection in several steps, and that's it. These models actually have some known theoretical limitations about what they can learn, so they're actually very simple patterns that they never can learn to generalize from, and they can at best memorize in these cases, in which means that they would need to see all possible combinations of inputs to produce the correct answer, which is again related to what Brandon was talking about before. When it comes to this generalization speed or the learning speed, the current state of machine learning is nowhere near the generalization speed of humans who actually can infer the patterns at a much higher level abstraction than the neural networks typically can represent, at least the ones that are currently used. So is actually deep learning useful for AI? Well, we don't really know. It can be actually a component in AI, but I think that pretty much everybody who works in the field for long enough doesn't think that just basically big neural network trained on a lot of data is going to solve the whole AI in the full sense, like of this human level AI. Still, you may see in the news like a lot of claims that we did achieve tons of progress in the last 10 years, but you should realize that the core of the recent improvements have been simply bigger training sets. So there's more money, more training data that can be produced for different tasks, and for tasks that we could already solve like 5 or 10 years ago with some reasonable performance, like say speech recognition, machine translation, we can solve them now better because we have models that are bigger, they are trained on more data, and they can generalize a bit better because neural networks are actually able to model wider range of patterns in the data than the techniques that they did replace. For example, in the case of language modeling that I've been working on, neural networks replaced Engram models that were considered state-of-the-art for like 30 years. There's this progress that a lot of the community realizes, the research community realizes that the strong supervision where we need to have the labels produced by humans is unrealistic for achieving AI, and for that reason many people are now like looking into reinforcement learning, which can be an alternative. In this case, we don't need to say what is actually a correct label for every training example. We just provide to the system some signal that should tell the system whether it's doing something right or wrong. So you can imagine that, for example, if you like this game playing system, and when it gets, for example, some extra points, then it will get a positive reward, and it can somehow extrapolate from this reward that it did something right, and kind of like strengthen its behavior so that it would repeat a similar decision next time. And the other way around, when it gets the negative reward, it tries to figure out what it should be doing differently next time. So it's actually much less supervised. You don't need to tell the system what it should be doing. You are just saying to the system when it does something right or wrong, and it has to figure out on its own what needs to be done. So it's like more general than the supervised learning on its own. The other interesting topic that is like part of the roadmap to AI for many people is the unsupervised learning. Although it's often a little bit confusing in the sense that often people see unsupervised learning as simply like a problem where you get the labels from the data themselves. An example can be language modeling. You can still use the supervisedly trained deep networks for language modeling, where the supervision will actually not not come from the human annotators, but from the data itself. You can take, for example, the whole Wikipedia, and you can try to predict every word given its preceding words, like the history in which that it precedes the word, and that's basically the core of statistical language modeling. So you don't need the labels, but you can still apply the same techniques as for the supervised learning. Or you can do the data clustering. You can, for example, learn again in a completely unsupervised way. For example, word vectors, like for people who know this, these things that we've been working on, like word2vec, then you can actually learn this again from the whole Wikipedia. Then you can run k-means clustering on top of these vectors, and you basically get some like insight into the data. How is it organized and structured? There are people who are thinking of doing pretty much the same for computer vision, where there are some plans. For example, Jan Lekan believes that we can get some interesting insight into AI by modeling videos, where we would be predicting pixels based on the preceding frames. And then the belief is that if you build a really good predictive model, then this predictive model needs to be able to kind of like model the real world to a great detail, so that it would know what will happen in the next few seconds in the video. That's basically what many people mean by unsupervised learning. I think that it would be also good if we would consider the unsupervised learning as something even like less supervised, in the sense that we may forget about these target vectors in neural networks completely, and there are actually techniques that can be considered in some sense even less supervised. And that's, for example, the evolutionary techniques that used to be popular like 20, 25 years ago. They actually were not very successful, but the idea is very simple to explain. Usually start with some population of models that can be initialized randomly. You pick the best subset of this population, you copy it to the next generation, and you also create some extra copies of the most successful individuals or models with some random mutations, which means random changes, and then you repeat this iteratively, and this approach is supposed to like sort of like emulate what evolution is doing, and this is actually less supervised than the previous ones, because the models don't usually even know what they are doing right or wrong. There's like some fitness function that's just like measuring which solution is better, and that can be actually using even like completely like discrete features. The models themselves don't have to be differentiable, as is the case for many of the models from the previous sections that I was talking about. So they don't have to be continuous. We can consider much wider range of models, and we can even get less supervised than this by even forgetting about the fitness function, and that's what some people from like artificial life community are exploring, how we would even like define some dynamical processes that would have this increasing complexity. That's actually a very interesting topic on its own, like whether we can develop some artificial system that has like this open-ended complexity that can increase in complexity indefinitely, because that really seems to be like the core of life on Earth, that there's no upper bound for the complexity. And even for us humans, even for our language, there's actually a lot of systems that can be seen as some evolving dynamical systems that do not seem to have any concrete goal, but are increasing in complexity. Actually, there will be like I think a full talk about this in the afternoon by Ken Stanley, who will like explain you much more about the ideas, why these ideas are actually cool to consider as like research problems. Because again, the interesting part here is that even if it's actually not that hard to define these goals, we don't really have a system that would be like open, like in this sense. Really, like if you look at the most successful examples of reinforcement learning, artificial neural networks, deep learning, it's pretty much always the same story. You basically update the weights of the model in like many epochs of training, and the changes of the weights are getting smaller and smaller, and at the end you stop the training, you get a fixed model that is frozen with all the parameters that is used at test time as it is. If you want to change some conditions a little bit, you have to throw the model completely away and retrain from scratch a new model. That's actually what Brandon was talking about. If you change the rules in some game, for example, just slightly, you have to basically start learning the models from scratch. It's very like unsatisfactory in some sense where we are so far. So I think that the challenges for our generation is actually to come up with some AI complete goals and forget about optimizing tasks, or forget, like, I think we already solved more or less some tasks to acceptable degree of accuracy, like the speech recognition, machine translation that have been proposed as like the big tasks like 30 years ago. We already know in many domains how to solve them well enough, and I think that the problem is becoming more like engineering problem in some sense. I don't mean it badly, but really like in many of these applications, the best answer to how to improve accuracy is to just get more training data. Just pay people some money to annotate more examples, and you will basically see speech recognition accuracy going up, and often that's actually just enough to get to acceptable level of performance. So I think that as a research community, we should be setting up more ambitious goals and try to work on something that would be much more like AI complete, which is a term that means that if you solve AI complete problem, you actually solve all the problems from the AI category, which I think is actually the right goal to aim for now. So we did actually propose, like in this paper, a roadmap towards machine intelligence, kind of like a crude plan how we can actually possibly get to machine intelligence in some distant future. We try to limit the complexity as much as we could, but still I think that the plan is totally out of reach to be finished anytime soon. So we did consider like some simulated environment where we have a robot that should be able to learn through communication how to perform some tasks with increasing complexity. Actually, that is also what Marek was talking about in the first talk. The plans here are quite similar. And the interesting parts here are that they're like, if you look at the tasks that we are considering as a human, they seem to be completely trivial, but for the machine learning techniques that, again, have to be retrained whenever you change the tasks slightly, exactly the incremental learning is the problematic topic that nobody knows how to solve. So I think that the challenges for our generation is to like to think more widely, and maybe we can take as inspiration for AI, not just like trying to simulate the human brain or human cognition, but maybe all like brains together, and maybe we can even extrapolate what are the patterns behind all the intelligence. Maybe we don't need to see intelligence only at the level of individuals, but maybe it can be seen that even life in some sense is intelligent because it's able to basically improve on its own. So maybe actually evolution is a very nice inspiration that currently is out of the mainstream of the research community, and I think that, as I said in the beginning, often the breakthroughs are not in the mainstream, not where everybody is searching at the moment. So I think that there's actually quite a few interesting topics like artificial life and fractals and so on that basically have this emergent complexity that we don't observe if in the case of neural networks, and that we believe actually should be present in this human level artificial intelligence, because like, as I said, there should be no boundary for intelligence. There should be like the possibility that these models will be becoming smarter and smarter and bigger, and it should not be these converging algorithms that just get to some good score at some one game and then just stop basically doing anything. So I think that's really like a challenge for us, like how to address these topics. I think that it was already said in the previous talks that we really want to have more generalization. I think that I can try to explain it better, or like maybe from different angle, that often people are like confusing these terms, like if you really are increasing amounts of training examples that you have, or amount of samples that the model sees during the training. It often is the case that these models are just memorizing all possible combinations of input features and corresponding labels. Generalization really means that you should be able to learn some higher level patterns, maybe some compositional patterns, and generalize much faster. Maybe even like easier to understand this is by considering the incremental learning, which is like some very old name that actually the same idea actually has multiple names. You can also call it transfer learning or like compositional learning, hierarchical learning. There's many names, but the logic is what I've been already slightly talking about. Basically, when you teach current state-of-the-art machine learning techniques to perform some tasks, and then you expect that it should be easier to retrain the system or adapt the system to perform some slightly more complicated tasks, similarly as we humans learn when we go to school and we are introduced to more and more complex topics, and we are storing in our long-term memory what we learned before, and we can base our knowledge on what we've learned before. That's exactly what the current techniques are completely unable to do. So often it's the case that trying to learn slightly more complicated problem after learning the simpler one is actually taking you longer than learning from scratch. Basically, there's no no transfer of the knowledge between tasks on the higher level, on the algorithmic level. If you, for example, teach a neural network how to add numbers together, and then you will want it to also understand how to subtract numbers, then there's no transfer of the knowledge, and you basically start from scratch, or even worse, you have to completely forget what you've learned before and retrain the model. So it's like going against the intuition of learning. So maybe even the word learning is currently overrated in the sense that the models that we have are more like nearest neighbors approximators, and they're like memorizing the training examples much more than they are doing anything that we could call learning. Then I think that the goals that I already mentioned, like that would be great to work on, that can maybe replace the previous tasks that already are solved, can be like how do we evolve communication, how do we build chatbots that would be able to actually help people and that will actually understand the conversation. These are like the big goals for us, and I think it would be great if the researchers would be trying to build frameworks how to approach these problems in the future. So to get back to the original question, to finish the talk, when shall we achieve the human level AI? I would not even try to make a guess, because so far, in my opinion, we have like great applications of statistical machine learning that is actually very useful in many tasks, but I wouldn't call these artificial intelligence when it comes to the human level AI. I think we are still pretty far from it. I would be also like somewhat optimistic as Marek that it can basically take maybe one or few ideas to come up with the next breakthrough, and nobody knows when will this actually happen. But because I've spent so much time in this field already, and I see like very few breakthroughs that are real, and much more of the breakthroughs that are kind of like just new names for the old tricks, then I think it will actually take quite some time, and some smart people who will come up with probably quite radically different ideas about what learning is and what even intelligence is. And last, slightly philosophical idea, I know that people at these places also are sometimes worried about the AI safety. There are these arguments that maybe we should not develop AI because it's going to destroy us, like all these movies about killing robots and so on, and AI competing with humans and replacing us. I think that's really like something that is not what we plan to achieve. It's more like a part of some science fiction movies that would be actually quite boring if they would be about some happy AI that is helping us. Nobody would go to see these movies. So I think that when it comes to AI safety, we can even like look at it from the other side, which I actually didn't really see discussed much, which can be like, what if actually not achieving AI is the biggest existential threat for humanity? Because I think that as the technology is getting increasingly more more complex. We are producing more and more like artificial substances, like chemicals that get into the environment. We as humans are actually very bad at making predictions what will happen like in some distant time, like say 20, 30 years from now, if we make some decisions, and maybe actually developing AI that would be helping us to become basically much smarter on our own, AI that would be basically part of us in some like symbiotic relationship. Maybe that's actually the way how we can avoid some possible disasters in the future, and in that case actually working on AI is like very important for all of us. So that's one of my crazy predictions for the end of the talk, so thanks for the attention.
Okay, the man with the iPad is back. Mm-hmm. Let's start on that one, and I'm desperately trying not to go for a Song of Ice and Fire meme here. You've talked about the inflated expectations from AI, Lucas Lienhardt writes. Do you think another AI winter is coming?
Well, it's a different situation than last time when it was like, I think AI winter sort of happened maybe like twice. And I think that we are actually right now at the AI summer, which is the opposite of AI winter, but it has also like its problems. The AI winter means that basically whenever the expectations are overhyped, then like the real people become kind of like pissed off, and they start talking about not nicely about like some crazy startups that are promising to solve everything, and then the funding basically disappears, and people have to move on to work on something else. So that's actually what happened, for example, when Marvin Minsky did write a book about theoretical or mathematical limitations of neural networks, which was actually completely right in its conclusions. Just some people did see the book as the reason why the funding stopped, but I think it was actually the other way around. It was the people who did make the crazy claims who did actually cause the winter. So I don't know if it's going to happen again. The situation seems to be somewhat different in the sense that at least the applied machine learning that I was talking about actually has tons of value, and somehow applied machine learning is currently seen as part of AI, and in that case, definitely not all of AI will disappear, because there is this useful part that actually makes money for like all these big companies like Google, Facebook, Microsoft, and so on. So definitely part of AI will stay. I think that if this AI summer or like the hype phase or like gold rush phase will actually get more like regularized, it would be only good for the research, so that people can forget about like these hypey claims when some new startup is looking for funding and it's promising things like crazy. So I think that if things would become more like calm and the community would not double in size every year, it would be actually good for research, and that's probably gonna come in the near future.
I like it how the AI summer escalated into the hype, into the gold rush. Then Hanna Kalibodova originally posted for the previous talk a question which I think still perfectly applies. Hanna, are you anywhere around?
There.
Ah, there. Okay, up there. Hey. So, what main difference do you see in training AI in things designed by humans for humans, and in understanding the nature in a human way?
Understanding nature in the human way. Well, there's of course like this other thing that if we want to develop AI and like human level AI, then we as humans have tons of prior knowledge that's coming from different sources. There's definitely like a culture that is influencing our intelligence and our decisions a lot, and then there's of course a lot of information that we did inherit from the previous generations. So talking about like general intelligence is like talking about some like alien life form that completely like does not share the culture and instincts with us. And sometimes I think that if we would really develop AI that would be based purely just on mathematics, it would be in some sense kind of like autistic AI, so that you can think of it as some AI that doesn't really share much with us, and it can live in kind of like its own world, and just connecting with it can be somewhat difficult. So I think that's one of the possible obstacles that I also see that sometimes people are making this big jump that when they work on AI, they just want to work on the most exciting problems right away. And I think that actually the difficult part of AI research will be like how to go over this phase when we have something like really small and just try to make it kind of like understandable by humans, like so that it would be AI that we can like efficiently communicate with. I think that the first step is just making AI that can understand in the right way very basic vocabulary of say 10 words is gonna be much more work than scaling this up to like understanding tens of thousands of words. So I think maybe that answers part of the question.
Okay, final question before a few organizational announcements and your caffeine break. Olivier Georgeon, Olivier, where are you? Over there. As a goal for our generation, what do you think of achieving animal-level AI? Would you consider it a milestone towards human-level AI?
I think that that's like almost the same like for some of us, that animal intelligence and human intelligence, I actually think that the principles are basically the same because we are also animals. And I think that there are, of course, like some differences between humans and animals, but that especially comes from the fact that we are actually able to transfer what we've learned to the next generations through the language, while most of the animals, not all of the animals, but most of the animals don't do this, and they rely on some limited learning in their lifetime and inherited instincts. So I think that the power of human intelligence comes from this fact that we can basically transfer what we've learned and teach the next generation the topics. But otherwise, I think that the principles behind animal intelligence and human intelligence are basically the same thing. And as I said, we are basically animals too.
Okay, let's thank Tomas again.
Thanks.